As you know that a Kaplan turbine is an axial flow turbine, and which is particularly suitable. Uh, since it works on a low head, it requires a large quantity of water to develop a large amount of power as compared to the Pelton turbine, because Pelton turbine works on a high head and requires less quantity of water to develop the same amount of power. So it is also classified in under the reaction type of turbine, where the flow enters radially and operates in an entirely closed conduit from the head race to the tail race. So this is the figure of the Kaplan turbine, where the water from the penstock is brought to the skull casing, and then it will be guided to the guide vanes, and from the guide vanes the water passes and then will turn at 90 degrees and moves axially, that is parallel to the axis of the rotation. So hence it is known as an axial flow turbine. So the here the shaft consists of here, which is connected to the boss or the hub. On the boss or hub there are 4 to 6 runner vanes which are mounted. So then after water passing through the through the runner vanes will move into the tail race, to the tail race through the draft tube. Okay, so this you can see that the draft tube is the lower end of the draft tube is immersed in the tail race. So here these are the component parts of the Kaplan turbine. So where it consists of the scroll casing, the guide vanes, and then we have the runner vanes, and also we have what is known as the boss or the hub, and then finally the draft tube. So here this the diameter, so this is that is known as the capital D is known as the diameter of the runner, where small d is the diameter of the hub or the boss. Now since the flow moves out axially, so here the to calculate charge, so we have discussed things. So now the discharge flowing through runner will be now pi by 4 into d square minus small d square into velocity of the flow. Here velocity of the flow is nothing but the velocity of flow at the inlet. So you also know that since the inlet and the outlet are the same distance from the central axis of the rotation, so tangential velocity at the inlet and outlet is equal to pi dn by 60, and also the velocity of flow at the inlet and the outlet are same. So that's the reason why Vf equals Vf1 is equal to constant. Here in Kaplan turbine, the discharge is radial, always radial at the outlet. So therefore it moves out radially. So therefore beta is 90 degrees and hence Vw1 is equal to 0. So therefore when it moves out, so there the Vr1 is in the tangential direction to the vane. So here it moves out in at right angles to the direction of motion of the vane. So beta is 90 degree. So that's the here we have Vf1 is equal to Vf. So yeah, since the water comes out, so the vane would have moved by some distance, so the water will come out in this direction. So here since the inlet and outlet are at the same distance from the axis of the rotation, so tangential velocity the outlet will be equal to tangential velocity at the inlet. So what is work done? Since Vw1 is equal to 0, so work done per second is rho AB. So Vwu plus or minus Vw1 U1. Since Vw1 is 0, so it is rho Q into Vw into U. So now you know that hydraulic efficiency, which we discussed in the Pelton wheel chapter. So we have work done per second divided by the water power. Here there is no nozzle which is fitted at the end of the penstock. So that's the reason why. So we are calculating the water power as so WQ into H. So here it is nothing but hydraulic efficiency work done per second divided by water power. So work done per second is rho Q VWU. So WQH divided by WQH. So here say what is specific weight? It is rho into G. So therefore the Q gets cancelled out. So therefore rho gets cancelled out. So therefore hydraulic efficiency is VWU GH. So overall efficiency is nothing but the shaft power divided by the water power. So therefore it is P by W Q into H. Sometimes in the problem we have what is known as a speed ratio. So speed ratio is nothing but U by V. So here it is nothing but U by root 2G H. And flow ratio is, because the flow is constant, so Vf radially moves out. So Vf by root 2 GH is nothing but the flow ratio. So if these values are given, you can make use in calculating the tangential velocity as well as velocity of the flow. Now we'll take a problem on Kaplan turbine. So a Kaplan turbine produces 60,000 kilowatts under a head of 25 meters with an overall efficiency of 90%. So we have to take the speed ratio is 1.6, flow ratio is 0.5, hub diameter or boss diameter is 0.35 times the outer diameter. So to determine the diameter and the speed of the turbine. So here P is 60,000 kilowatts, head is 25 meters, overall efficiency is 90%. So given U is, that is speed ratio is 1.6, so it's 1.6 times root 2 GH, whereas velocity of flow is 0.5 times root 2 GH. Given D equals 0.35 times capital D, you have to find diameter of the runner as well as the speed. So in the first step, we have to find the discharge. So we can make use of overall efficiency. So overall efficiency is P by WQH. So power is, you can convert into watts. So therefore specific weight is 9810 into Q into 25. So that gives discharge as 271.83 meter cube per second. So now given the speed ratio, you can calculate U by equals 1.6 times root of 2 into 9.81 into 25, which gives 35.44 meter per second. Similarly, the velocity of flow can be calculated as taking the flow ratio, which is 0.5. So 0.5 times root into 9.81 into 25, which gives 11.074 meter per second. So since the discharge formula is known, so we have Q is equal to pi by 4 capital D square minus small d square into Vf. So we can substitute the value of discharge. Similarly, d square, here the hub diameter is 0.35 times the capital D, so square whole square into 11.074. So taking out d square and solving, so we'll get d as 5.97 meters. So you know that the hub diameter is 0.35 times capital D, so that gives 2.09 meters. So knowing the tangential velocity and knowing the diameter, so we can calculate U equals pi dn by 60, where n can be calculated, which is the speed of the runner. So therefore speed comes to 113.4 rpm. A similar problem again, we have an hub diameter which is 0.35 times the diameter of the runner. So the head is 15 meters, so therefore the head is 15 meters. Turbine is running at 110 rpm. So the vane angle is given at the extreme edge, so that is nothing but phi is given. So okay, vane angle is given and the flow ratio is 0.6. So we have to find the diameter of the runner, diameter of the hub, as well as the discharge. So given the flow ratio, we can calculate Vf. So Vf is 0.6 times root 2 GH. So H is 15 meters. We get 10.29 meter per second. Now you know the discharge is always radial at outlet. So Vw1 is 0. So therefore this writing the outlet velocity diagram. So therefore since Vw is 0, so it moves out radially outwards. So therefore it moves out in this direction. So where Vr1, so this is U. So now you can using, so U is equal to U1. So therefore tan phi is equal to Vf by U. So knowing phi equals 18 degrees, Vf as 10.29, so we can calculate the tangential velocity. So U is equal to U1 is equal to 31.67 meter per second. So knowing U, you can calculate the diameter. So therefore U is equal to pi dn by 60. So therefore U is 31.67, whereas D is to be determined. N is 110 rpm, so that gives D equals 5.5 meters. Therefore the diameter of the hub is 0.35 times the outer diameter, which comes to 1.925. So then discharge can be, knowing capital D and small d, so we can find out the discharge, which comes to 214.42 meter cube per second. So a Kaplan turbine is working under head of 15 meters, so therefore 15 meters, and develops a power of 7357.5 kilowatts. So P is 7357.5 kilowatts. But here the outer diameter as well as the hub diameter is given as 4 meters and 2 meters respectively. But the guide blade angle at the extreme edge, that is guide blade angle is always at the inlet. So alpha is given, which is 30 degrees. So then the hydraulic efficiency is 90%, whereas overall efficiency is 85%. So if the velocity of whirl is 0, so they did not give the always discharge is radial at the outlet. So VW1 is always 0. So we have to find runner wear angles, that is theta and phi. So also we have to find the speed and the specific speed. So the first step is, because the overall efficiency is given, so and power is also given, so that enables us to calculate the discharge. So therefore we have overall efficiency is 0.85, so power is 7357.5 into 1000 to convert it to watts. So specific weight of water is 9810 into Q into H is 15, so therefore we'll get discharge as 52.58. So now, knowing the diameter as well as the hub diameter, so we can substitute in discharge formula to get the velocity of flow. So therefore, since the discharge is known, which is 58.82 equals pi by 4, 4 square minus 2 square into Vf, so therefore velocity of flow can be calculated. So before we write the inlet velocity triangle, so here we know that the component of V is Vf and Vw. So the radial component is the perpendicular to the motion of the vane is Vf, whereas in the parallel is Vw. So now, knowing alpha, so we can calculate Vw. So therefore tan alpha is Vf by Vw, so which gives Vw 10.82 meter per second. So now we can draw this diagram, that is inlet velocity, unless we know the value of u. I have to find out here u is less than Vw or greater than Vw. So that's how should be. So that's the reason why it is not plotted in these initial stages. So using hydraulic efficiency, we know that hydraulic efficiency is Vwu by GH. So therefore hydraulic efficiency is 0.9. So Vw we already calculated as 10.82 into u by 9.81 into 50, so that gives 12.24. So since u starts from the tail, so it is exceeding 10.8, so therefore it will go up to here. So that's why it is crossing this point. So therefore u is up to this point, and then line joining from tip to tip is nothing but Vr. So if u was less than Vw, so then it would have stopped like this u, so then this would have been Vr. So like then this angle would have been theta. But this is not the case. So this is the case where you have u greater than Vw. So therefore the angle of vane at the inlet becomes an obtuse angle, that is theta. So in order to find theta, so we'll name this as theta dash. So tan theta dash is Vf by u minus Vw. U So that's how we calculated. So that's why theta dash is calculated. So that theta will be equal to 180 minus theta dash, which is 102.8 degrees. So now we know, since the discharge is radial at the outlet, so we can always plot this outlet velocity triangle and get from tan phi is equal to Vf by u, because Vf is known, u is known, so that gives the angle that is the runner vane angle at the outlet. So to calculate the speed of the turbine, we know u is equal to pi dn by 60. So knowing u, knowing d, we can calculate n, which comes to 58.47 rpm. This is also told to calculate the specific speed. So specific speed is the speed of a geometrically similar turbine when working under head of 1 meter will develop 1 kilowatt power. So that means if you construct a geometrically similar model as the prototype and then operate it under a head of 1 meter, it will develop 1 kilowatt power. And if you find out what is the speed of that model, so that is nothing but the specific speed. So therefore specific speed is given by n root p h to the power of 5 by 4, so which comes to 169.9 rpm. So here you have to be careful that P has to be in power developed in kilowatts. So therefore while substituting in n root P, so this has to be in kilowatts. So taking a similar problem, we have as the previous problem. So here the head develop is 20 and the power is 11,772 kilowatt. So outer diameter is given 3.5, whereas the hub diameter is 1.75. So guide blade angle, that is alpha, is 35 degree. Hydraulic efficiency is 88%. Overall efficiency is 84%. We have to find theta and phi and also speed of the turbine. So hence repeating the same procedure. So from overall efficiency, P is equal to WQH. So knowing overall efficiency, knowing the power, convert into watts, multiplying by 1000 divided by specific weight has to be in Newton per meter cube, that is 9810 into cube to H, which is 20, so that gives 71.428 meter cube per second. So knowing the discharge formula, so that is Q is equal to pi by 4 into d square minus small d square into Vf. So we'll get discharge, substitute here. So substitute the value of d, again the substitute the value of hub diameter, we'll get velocity of flow. So velocity of flow is around 9.904 meter per second. So now again the same, following the same procedure, writing the components of V in the radial direction, which is Vf, and the horizontal direction is Vw. So we can calculate Vw. So tan alpha is Vf by Vw. So therefore we get, because alpha is known 35 degrees, so Vw can be calculated, which is 14. Now I want to know that, I have to calculate the value of u. So I want to see that whether it exceeds Vw or it will be less than Vw. So now using hydraulic efficiency, so which is VWU by GH. So hydraulic efficiency is 0.88, VW is 14.14 into U, which has to be calculated, we get 12.21. So here VW was 14.14, so therefore U starts from the tail of V and stops because it is less than. So now the line joining from tip to tip is nothing but VR. So this theta will now be acute angle. In the previous case, theta was an obtuse angle because U was greater than VW. So in this case, tan theta as usual is VF by VW minus U. In the previous case, it was U minus VW. So theta is around 79 degrees. So now writing the outlet velocity triangle. So therefore tan phi is VF by U. So hence phi can be calculated because VF and U are known. Similarly, from U is equal to pi dn by 60. So we get the n, that is 66.7 rpm. So you can also calculate specific speed by n root p h to the power of 5 by 4 and get specific speed for this problem also. So this is about the Kaplan turbine and the various problems that are associated with the Kaplan turbine.